Fine, let me join from iPad also. All right, I guess today we only have 3 students and we'll start now. So welcome everyone to the week 4 live session on the course Semiconductor Devices and Circuits. Just a second. Uh, NPTEL NOC24 EE-143 tutorial. The instructor for the course is Professor Sanjeev Sambandan from ISC Bangalore, and I am the teaching assistant. The schedule for these sessions is every Sunday 5 p.m. to 7 p.m. And yeah, let's quickly go through the guidelines. In case you have any query, you can either ask in the chat window or just raise your hand and unmute yourself. And when you don't intend to speak, please make sure your microphones are muted. I forgot to switch on the video. Wait, why am I not? Is my video? I mean, yeah, it's visible now. Fine. So let's try to make this an interactive session. So I appreciate your cooperation for the same. Uh, I'm sure you would have kept pen and paper ready along with a calculator. The session recording link and the lecture notes will be shared by the NPTEL course team in the due course of time. So what are the prerequisites? Prerequisites include the lectures covered in the last week, which are following the recombination and generation. I mean, the topics are following recombination and generation. We learned about charge transport and the continuity equation. And before, I mean, watching this session or attending this session, I hope that you already have attempted the assignment 4 first. So nothing much for brief recap. I'm sure you would have already gone through the lectures. We learned about different types of recombination and generation processes. Then we saw in detail the charge transport and the, I mean, one of the important equations, the continuity equation, right? So with that, we'll start with today's first problem. So the first problem is the electron concentration varies linearly as shown in the above figure. The concentration of electrons at x equal to 0 is n and x equal to L is 0. Fine. You need to calculate the total number of electrons present in the material. Given cross-section area is A. Okay. Please attempt this one and let me know which option is correct. I guess I'll start doing it myself now. So what are we given? See, we are given that this electron concentration varies linearly, right? So we can model this n of x by a plus bx, right? Where a is this intercept. So now we know following things, right? Number one is that we are given that n of 0 is equal to n, right? Because when x equals to 0, we have n, right? And that's why. And similarly, at x equal to L, it's 0, right? N is 0. So can we determine A and B from this information? Yes, because when we put x equal to 0, your, we will get N is equal to A. If anyone disagrees, he can raise a query. Otherwise, I'll continue. Similarly, N of L, which is equal to 0, is equal to A plus BL, right? So what does this imply? This implies that your B is equal to minus N over L, right? So we determined these two constants. But we are interested in total electrons, right? Because in the question it was asked that we need to find or calculate the total number of electrons that are present in the material. The cross-section area was A. Now, what is your n of x now? Let's write the expression for n of x. Since now we know A and B, our n of x takes the following form. It would be n, I can take n common, and then it would be 1 minus x by L, right? And x varies something like this. Fine. And we have total electrons that is equal to concentration multiplied by volume, right? And this is equal to A integral 0 to L n 1 minus x by L dx, right? And yeah, what I did was I integrated this n over x from 0 to L and then multiplied that by the cross-section area, because that is effectively what would give me the total number of electrons. This would be A n n L minus x square by 2L. You can double check this. This would be A n L minus L squared by 2L, right? So your total electrons would be equal to A L n by 2. Just, sir, please explain the above equation. This one, I got this one by using A equal to n and B equal to this. Put that and take the n common, you will get this. Fine. This is simple. Fine. Let's move forward. So which option is correct? The correct answer is option this. Option C, right? Option C is the correct one. Now let's move forward. Question 2. Attempt this one now. A semiconductor has the following properties. Your DN is 25 centimeters square per second. dp is 10 centimeters square per second. Tau n0 is your 1 microsecond and tau p0 is 0.1 microsecond, right? The semiconductor is p-type with Na equal to 10 to the power 17 per centimeter cube, and it's held in equilibrium for t less or equal to 0. At t equal to 0, an external source is turned on, which produces an excess carrier at the rate of 10 to the power 20 centimeter cube per second. At t equal to 2 microseconds, external source is turned off. You need to determine what is the excess electron concentration at t equal to 2 microseconds. So how would we approach this one? Anyone? Anyone? Which equation should we use? All right. I guess I'll do it myself then. So since it is a p-type, uh, minority carriers, would they be electrons or holes? It would be electrons, right? So the continuity equation will be, how will your continuity equation look? Your continuity equation would look following. Your continuity equation would look following since it's p-type with minority carriers as electrons. So it would be dn dou 2 delta n by delta x square plus mu n e dou by dou x delta n plus gl minus delta n by tau n0 is equal to dou by dou t delta n. Right? This is your continuity equation. Now, we can actually simplify this continuity equation. Why? We can simplify it because since it's a uniform generation, right? Since it's a uniform generation, then everywhere equal number of carriers will be generated, right? Since that is the case, this term would go to 0, right? I'll write that this is what? Uniform generation, right? And also the second term is 0. Can someone tell why? Why is the second term 0? The second term is 0 because the electric field is 0, right? There is no electric field. So that simplifies our continuity equation considerably, right? What are we left with? I'll write the remaining part. GL minus delta n by tau n0, that is equal to dou by dou t delta n. Right, after that, then we can write following thing. So I can rearrange this and get this dou by dou t delta n plus delta n by tau n0, that is equal to GL. Now you can compare this with standard equation, this dy by dx. Remember we had, if we had this kind of differential equation dy by dx plus py equal to q, we used to compute integrating factor, right? I'll do the similar thing. What I'll do is, in this case my p is 1 by tau n0, and what is my this q? The q is gl, right? So what is the integral p dt? Integral PDT is nothing but T by tau n0 simply, right? And your integrating factor, that is equal to exponential of this integral PDT, right? So this is your exponential of T by tau n0, right? So we write following. We write y times integrating factor, right? How we solve for this? Y times integrating factor, we write y times integrating factor, that is equal to integral q times integrating factor to be integrated obviously with respect to x plus c prime, right? If you compare it with our case, we have following thing. We'll have delta n, integrating factor is e to the power t by tau n0, that is equal to your integral gl e to the power exponential of t by tau n0 dt plus c prime, right? And delta n uh, exponential of t by tau n0, that would be equal to your tau n0, right? If you solve the integral, you'll get following gl exponential of tau by tau n0, and you'll have this plus c prime. Let's keep this as your equation A, right? Now that we have written this at t equal to 0, what do we have at t equal to 0? At t equal to 0, our delta n is equals to 0, right? So 0 times 1 is equal to cn0 gl. Just a second. Yeah. Hmm. This would be plus c, and in other words, our this constant c would be minus tau n0 by multiplied by gl, right? Yeah. So what does that give us if we substitute back? That gives us the following. Then let's box this one as well. It's delta n exponential of t by tau n0, that is equal to tau n0 gl exponential of t by tau n0 minus tau n0 gl, right? So your delta n would be equal to tau n0 gl 1 minus exponential of minus t by tau n0, right? This is the solution of that differential equation, right? Now your delta n is equal to 1 into 10 to the power minus 6 into 10 to the power 20. 1 minus exponential of minus 2 into 10 to the power minus 6 whole divided by 10 to the power minus 6, right? So this would be your delta n. I mean, these quantities, the constant values were already given in the question, right? I use them. Now delta n is equal to 10 to the power 14 multiply by 1 minus exponential of minus 2, right? That means your delta n is equal to 8.65 into 10 to the power 13 centimeter per cube. So which option is correct? The correct option is option A, right? Option A is correct. Yeah, we are done with this now. So now the next question, right? What about this one? An intrinsic silicon wafer, it is doped with 10 to the power 16 per centimeter cube donors, right? And your 10 to the power, firstly, tell me one thing. Uh, this we computed at t equal to 2 microseconds, right? Because in the question we were provided that, right? See, we had to compute it at t equal to 2 microseconds, right? I did that, right? What about the case when t would approach infinity, the steady state? What would be the value of delta n of t as t approaches infinity? Can anyone write in the chat? What will happen steady state? I mean, although it's not asked in the question, but still, what will happen in steady state? Simple, right? If this t approaches infinity, this term would be negligible. We are left with this part. So for steady state at t equal to infinity, that would be equal to tau n0 gl. You can substitute the values and get the answer. So now moving on to the third one. So an intrinsic silicon wafer, it is doped with 10 to the power 16 per centimeter cube donors. 10 to the power 12 photons per second light is irradiated on the silicon per centimeter cube volume. You need to assume each photon generates one electron hole pair, right? Under this light illumination, location of the Fermi levels inside the silicon with respect to the intrinsic Fermi level are dash electron volt and dash as viewed by the electron and holes respectively. So yes, need to fill in the blanks, right? You can assume that the intrinsic carrier concentration is 10 to the power 10. I mean, assume this is, I guess I'll write this. This is 10 to the power 10. Fine. And your thermal voltage is 26 millivolt, right? So you guys can solve it at your end. I'll also do it at my end. Fine. So firstly, this is doped with donors, right? So what is the majority carrier concentration? Your majority carrier concentration would be N0, right? That would be approximately your donor concentration, which is nothing but 10 to the power 16 per centimeter cube. What about minority carrier concentration? Your minority carrier concentration would be P0, right? And by law of mass action, that would be Ni square by N0. That would be 10 to the power 20 because Ni is 10 to the power 10 whole divided by your 10 to the power 16. That is nothing but 10 to the power 4 per centimeter cube. Fine. Now, what is EFN minus EI? Right? That is nothing but KT ln of N0 by Ni, right? Which is nothing but 0.026 ln of 10 to the power 16 whole divided by 10 to the power 10, which is approximately 0.36 electron volt, right? This is the position of the Fermi level at thermal equilibrium, right? And similarly for, I mean, EI minus EFP, that would be KT ln of your P0 by Ni, right? Which if you compute, this comes out, if you use P0 as 10 to the power 4 and Ni as 10 to the power 10, this would be approximately again 0. What would this be? Wait. I guess there is a minus sign, right? There would be a minus sign. So that's why this would be 0.36 electron volt. Fine. Now, your Fermi level, is 0.36 electron volt above intrinsic level, right? And the light illumination, it creates light illumination creates 10 to the power 12 centimeter cube per centimeter cube electron hole pairs, right, per second. So therefore, your delta N is equal to delta P is equal to 10 to the power 12 per centimeter cube, right? Your N is equal to N0 plus delta N, and your P is equal to P0 plus delta P. This is 10 to the power 16 plus 10 to the power 12, and this is 10 to the power 4 plus 10 to the power 12, which is approximately 10 to the power 16 per centimeter cube, and this is approximately 10 to the power 4 per centimeter cube. So if we, find the position of the Fermi level after illumination, what will be the case when we, I mean, consider the after illumination case? In that case, your EFN minus EI, that would be KT ln of N by Ni, right? Which is approximately 0.026 ln of your 10 to the power 16 by 10 to the power 10, right? Which is 0.36 electron volt. Fine. And your EI minus EFP, wait, your EI minus EFP would be KT ln of your P by Ni, right? Yeah, and it comes out as 0.12 electron volt, right? So we have two different Fermi levels to capture this situation, right? And hence it's a non-equilibrium case, obviously, because we eliminated the sample. So which option is correct? The correct answer is option 2, right? Because the location of the Fermi levels inside the silicon with respect to the intrinsic Fermi level is, uh, I mean, as viewed by the electrons, it would be 0.36 electron volt, and as viewed by the holes, it is this 0.12 electron volt. So now we are done with this one as well. Now fourth one, the minority carrier lifetime of electrons in a certain semiconductor is 9 into e to the 9 e minus 12 seconds. The electron mobility is 350 centimeter square per volt second. Now, if the thermal voltage is 25 millivolt, the diffusion length of the electrons is dash. I'll start the solution. So solution for this is as follows. The minority carrier lifetime for electron. Okay, the minority carrier lifetime for electrons, that would be your 9 into 10 to the power minus 12 seconds, right? 9 picoseconds. What is your mu n? Your mu n is 350 centimeter square per volt second, right? What is your dn? Your dn is kt over q by, times mu n, right? This is your Einstein's relation. What is your diffusion length? Your diffusion length, that is equal to your ln, and that, just a second, that is equal to your ln, and your ln is equal to square root of this dn tau n, right? And this is nothing but square root of this kt over q mu n and your tau n, right? And this is simple. See, we were told to take this thermal voltage as 25 millivolt, right? I'll do the same. So I'll take this as 25 into 10 to the power minus 3, and my mu n is 350, and my tau n, that is 9 into 10 to the power minus 12, right? So your ln, that is equal to 88.7 into 10 to the power minus 7 centimeter. So what does this imply? Your ln is 8.87 into 10 to the power minus 6 centimeter. This is your diffusion length. So if you round this off, which option is correct? Option A, right? Let's move on to the next question now. A p-type semiconductor, it has 10 to the power 10 per centimeter cube uh, intrinsic carrier concentration, 2 into 10 to the power 16 per centimeter cube dopant concentration. If electron and hole mobilities are 1000 and 500 respectively in the respective units, the resistivity is the thing that we need to compute, right? Firstly, if you will look, I mean, what is resistivity equal to? In general, for a bar, for semiconductor bar, the resistivity would be equal to 1 by your P mu P Q plus N mu N Q, right? But it turns out in this question, one of them dominates over the other. So we'll be neglecting the other one. Which one dominates, we'll see, right? Okay, so what we are given is Ni is 10 to the power 10. This we know. Okay, Na, let's write that. So our Na, that is 2 into 10 to the power 16. This is p-type, right? So also mu n, that is given, right? Mu n is 1000 centimeter square per volt second. Similarly, your mu p, that is 500 centimeter square per volt second. And what is your n? N is Ni square by Na, right? That is 5 into 10 to the power 3. And your P, that is equal to 2 into 10 to the power 16. Now, as your P mu P is greater than N mu N, your rho is equal to, sorry, rho is approximately 1 by P mu P Q, right? And that is, right, because this one dominates. I mean, we do have that N mu N Q, but that is negligible. So if you solve it, you'll get this as 0.625 ohm centimeter. So that is your required answer, right? Your rho resistivity is 0.625 ohm centimeter. Now the sixth question. A semiconductor having an intrinsic carrier concentration of 10 to the power 10 per centimeter cube is doped with 10 to the power 15 per centimeter cube donor dopants. After doping, the Fermi level is located at EF0, right? The doped semiconductor is then irradiated with 10 to the power 20 photons per second, such that each photon impinging on the semiconductor, it leads to the generation of one electron hole pair. During this illumination, the Fermi levels for holes is located at EFP, fine, and the thermal voltage, we can take that as 25 millivolt, it's given, and your minority carrier lifetime for the holes is 10 to the power minus 6 seconds. The value of this EF0 minus EFP in electron volts, that is something that is of interest and we need to compute that. It is simple. How will I approach this question? See, your Ni is 10 to the power 10 per centimeter cube. Your Nd, that is 10 to the power 15 per centimeter cube. So therefore your P, that is your Ni square by Nd, would be equal to 10 to the power 5 per centimeter cube, right? See, let me make a diagram here. Your EC, your EV, your EI, this is your EF0. So your EF0 by minus EFI formula minus intrinsic formula, that is KT ln of Nd by Ni, right? So your in this is then equal to 0.025 ln of this is 10 to the power 5, right? Similarly, uh, the concentration rate, right? Uh, I mean the G generation rate is given by delta P by tau P, right? See here, uh, G is equal to delta P by tau P, and this implies that your wait. Hmm, okay, it's irradiated with 10 to the power 20 photons, so we can take delta P as 10 to the power. Yeah, we can take that. We can take delta P as 10 to the power 20. Oh, this is G tau P, right? And your G is 10 to the power 20 times your tau P. Your tau P is 10 to the power minus 6. So this is your 10 to the power 14, right? So what I got is 10, delta P is 10 to the power 14 per centimeter cube. Effective hole concentration, right? So your effective hole concentration, that is implied by P plus delta P, and that is 10 to the power 5 plus 10 to the power 14, which is 10 to the power 14 per centimeter cube, right? Now let's make another page. This is your EC, this is your EI, and this is your EVAC, I mean valence band level. And this is your Fermi level holes, right? Your EFP. So now again we'll write that EFI minus EFP, that is KT ln of Na by Ni, right? Where Na is your effective hole concentration. So this should be 0.025 times ln of 10 to the power 4, right? Yeah. So now what I'll do is I'll add two equations. I'll add this and I'll add this. See, when I'll add this and this on the left hand side, your EFI and EFI would go, right? What I'll be left with is following. I guess I should write this as B and this as A. Adding A and B. When you do that, you get following, right? You get that EF0 by minus EFP, that is 0.025 times ln of 10. Just do this calculation part. You'll arrive at this 9, right? So your EF0 minus EFP is equal to 0.518 electron volt. This part is done. Now question number 7. In question number 7, let's say we have been given an undoped intrinsic semiconductor. Now, if we dope this semiconductor with group 5 impurities at concentration of 10 to the power 20 per centimeter cube, and we obtain a doped semiconductor such that the conduction is completely dominated by electrons. Now I cut out the sample of a cubical shape of edge dimension uh, 1 centimeter from the doped semiconductor, and we tell that this resistance obtained when measured across the opposite faces is 0.1 meter ohm. The mobility of electrons in the semiconductor is, what is the mobility of electrons? We need to compute that. Q we can take as 1.6 into 10 to the power minus 19, that we know, right? So see, since it's group 5, I mean, I dope the semiconductor with group 5 impurities. Is group 5 impurity donor or acceptor? It is donor, right? So let me write this, otherwise we'll lose track. So group 5 impurities are donor impurities. What's happening? Why is it not working? Fine. So this implies that your ND is equal to 10 to the power. Something is wrong. Your ND is equal to 10 to the power 20 per centimeter cube. And your conduction band, conduction dominated by electrons. Your conduction dominated by electrons. It implies N is greater than P. So that is concentration of electrons is much greater than the concentration of holes, right? Your ND is N, right? Now sample is a cube, right? It's a cubical shape of edge dimension 1 centimeter. So it would be something like this, right? It would be something like this, 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 and this, this, and this, and this, and this. Right? And your RA to B would be 0.1 milliohm. Yeah, note this edge of cube is 1 centimeter. Right, so this is 10 to the power minus 4 ohm, right? And R is rho L by A, right? And your rho is 1 by Q n mu n plus p mu p, right? And this is approximately 1 by Qn mu n, right? So this implies R is L by A times 1 by Qn mu n, because this n Qn mu n dominates, right, over this Qp mu p. What does this imply then? This implies that your mu n is equal to L by A Q N R, right? And if you put in the values of the quantities that are given in the question, you'll get this value of mu n, right? Your mu n is equal to 625 centimeter square per volt second. Now, question number 8. Please try to attempt this one. In fact, this is referring to question 7 itself, right? Let's say the semiconductor obtained after doping is put to use in a system operating at 450 Kelvin. You need to find the value of the diffusion coefficient Dn centimeter square per second. Given value of kT at 300 Kelvin is 0.025 electron volt. Please solve this one. See your temperature, that is 450 Kelvin, given kT is your 0.025 electron volt at T equal to 300 Kelvin, right? So at 450 Kelvin, your kT is equal to, it's quite simple, right? It would be 0.025 times 450 whole divided by 300. That is 0.0375 electron volt. Your Dn is equal to kT mu n by Q from Einstein's relation, right? So your Dn, that is equal to 0.0375 into 625 all divided by 1.6 into 10 to the power minus 19. That is your 14.64847375 into 10 to the power 19. Then we have question number 9. Right. So question number 9, in question number 9, we have been asked that, yeah, let's say there is a machine that can set the mobility of the dominant charge carriers at will and without altering other parameters of the semiconductor. If you have understood the flow of the concept, you will quickly realize that, I can build a filter of the desired cutoff. Say I now decide to build a low pass filter with cutoff frequency say 10 kilohertz, right? But due to some error, I end up with a filter of cutoff frequency 12.5 kilohertz. Upon characterizing the semiconductor, the mobility comes out to be the value set on the machine. This means that there was an error in the fabrication at the doping stage. You need to find the ratio of the desired doping concentration to the doping concentration present in the semiconductor sample. Please attempt this one. Meanwhile, I'll also attempt, and let's see how our answers compare. So your cutoff frequency is 10 kilohertz. This is what we desire. But cutoff frequency obtained is equal to 12.5 kilohertz. Mobility is as desired. Right, from characterization. Low pass filter cutoff frequency. What is that equal to the expression? Low pass filter cutoff frequency. That is equal to 1 by 2 pi RC. Right. And now from this question, we know that the semiconductor is used to make the R, right? The resistance. And that resistance R, I'll write it. Resistance of the semiconductor, that is equal to L whole divided by A, and then your this mu n plus mu p times q. Right, then let's assume p is less than n, and your n is equal to nd. Right, then your r, that r is equal to L whole divided by A q mu n. Right, and that is equal to L whole divided by A q mu n d. Now I'll write, since our mobility, right? Since this mobility is as desired, the variation is due to doping density, right? So your F, that is 1 by 2 pi RC, that is 1 by 2 pi. Your R is L whole divided by A Q mu n nd times C. It is equal to A Q mu n nd whole divided by 2 pi LC. Right. Now if you take the ratio, right? If you take the ratio F desired whole divided by F obtained, right? That ratio is equal to, that ratio is equal to A Q mu n nd Obviously this ND is desired one, right? And here is 2 pi LC, right? Similarly, the factor AQ mu N ND, but this ND is what you obtain actually, right? And we have then 2 pi LC. What would this be equal to? See, everything would be cancelled, but this ratio ND by ND. In this case, this is the desired ND, and this is the one that we obtained, right? And that is equal to your 10 by 12.5, that is 0.8, right? So therefore, your ND desired by ND obtained, right? That is equal to 0.8. Right? This is the answer. So was this? Yeah, we are done with this one. Now, this is theoretical one, right? So which of the following statements is true with regards to the charge transport in a semiconductor? This is pretty straightforward, right? The diffusion current is independent of the temperature, whereas the drift current is strongly dependent in temperature. No, that is not true. The movement of the carriers can now, I guess it was disconnected for a while. So the third one is the resistivity of intrinsic semiconductor always increases with the temperature. Since the increasing lattice vibrations, they reduce the carrier mobility. No, that's also not true. The fourth one is the velocity of the carriers in a semiconductor at low electric field is strongly dependent on the effective mass of the carriers. Well, that is indeed true. The velocity of the carriers in the semiconductor does strongly depend on the effective mass of the carrier. So this one is the correct statement among these four. The 11th one is you need to select the true statements for the quasi-Fermi level. Should it be A, B, C, or D? This can be multiple selective type question. Okay, so I mean more than one options can be correct. So it turns out only option D is incorrect. Rest of the options are correct because the quasi-Fermi level, I mean, it's the generalized form of Fermi level. They allow us to compute the current in a device. That's also true. They are equal to the Fermi level at equilibrium. That is also true, right? Only the last one is incorrect, right? Hole and electron quasi-Fermi, they are related to each other. If we know one, we know the other. No, that's not the case. Question number 12, I'll leave as an assignment for you all. Try this out, right? A silicon wafer that is maintained at T equal to 300 Kelvin, it is doped with 10 to the power 15 per centimeter cube donor atoms. Light irradiating the wafer leads to a steady state photogenerated density of electron hole equal to 10 to the power 19 per centimeter cube. You need to assume that the wafer is thin compared to the absorption depth for the light so that the free carriers are uniformly distributed throughout the volume. What is the position of the quasi-Fermi for electrons below the intrinsic Fermi level? You need to only give the magnitude in electron volt. So this is assignment. Please try this out. Okay. This is your assignment. So this one is done. What about this one? Question number 13. In continuity equation, the change in the carrier density is it due to the flow of the incoming flux? Is it due to the flow of outgoing flux? Is it due to the difference of the flow between the incoming and outgoing flux? The correct answer is this one, right? I mean, although it is due to the difference of flow between incoming and outgoing flux, plus there is generation and mines recombination as well, right? That is what defines the change in the carrier density. We saw the continuity equation in one of the problems as well today. So yeah, that wraps up today's session. I'll be ending this session. Fine. Thank you.